project involves using axiomatic design to control the surface quality or the surface roughness of 3D printed parts. I'm Ernie Mello. To my left is Mike Burlide, and to my right is Michael Scanlon. Some objective in the rationale. The objective is to control the surface roughness of 3D printed parts, and when we talk about the surface roughness, we're talking specifically the peak to valley distances, which are represented here by the peaks RP, the valleys RV, and the distance that we're trying to either increase or decrease depending on the application is RT. So obviously if we're looking to make a smoother surface, we're trying to decrease RT. Trying to make a rougher surface, we're trying to increase the peak to valley distances. And the rationale behind this is it's one of the main problems associated with current 3D printing processes. As you can see here, we got 40 micrometers is approximately the surface finish that is produced by 3D printing, and it's poor comparatively to other types of rapid prototyping. And in case anyone has forgot about how important roughness is, this is a slide that was shown to us earlier in the term by Professor Brown, and for recycling, and it shows the importance of roughness, and we just wanted to stress that because as 3D printing tries to move into different applications, this is going to be important. We have groups trying to work on the strength of 3D printing, and as it is transferred on to different applications, it's going to be important to try to control the roughness in order to control these different performance parameters.
All right, so we're doing state of the art here. I decided to go through a couple of laser patents. The first one, the multiple station laser ablation process, was designed to cut small solar cells. This system incorporates both a measuring and cutting system on a very, very small scale to keep the surface finish of a small solar cell very, very tight to meet better tolerances. The other one was a micromachining with high intra-cavity Q-switch CO2 laser pulses. This system is a system that ablates high melting temperature metals with short high energy bursts from the CO2 laser. This is very good because CO2 lasers are relatively cheap, and creating something that could melt very, very high melting temperature metals is crucial because it can really only be done in castings and forgings as of late. I wanted to go over some commercially available laser cutters. You got two basic types of devices. You got your home or office one, which is the full spectrum laser, or you've got your massive industrial one, which is like an Ohio laser device. The Ohio laser is capable of cutting 1-inch thick plate stainless steel. The full spectrum laser is capable of cutting maybe a 3/8 plexiglass. So there's a big scale between the two of them. I just wanted to touch upon the scale between the available powers of lasers. We've got several different types of 3D printers. The cheapest one's going for around $500. Got a 6x6 creation table. It mainly uses ABS plastic, whereas the Object on the other side can sell for upwards of $20,000. It has a very large creation area, and it can create multiple materials at the same time and incorporate them all into the same design. This was a patent that we found recently that combined everything that we've been trying to talk about. This man, Alfredo De Angelis, he patented a multi-material rapid prototyping system which introduces elements of subtractive machining such as grinding, polishing, and milling. This system also has the capability to alloy, heat treat the parts it produces. However, the system was not completely modular and was designed to be completed by several machines, where you can see in the upper left-hand corner he did a flow chart of how this would work as a whole system.
We'll just move to the Eclair file for a second, because we're going to do it based on that. And here we are. So, thank you. Oh, yeah, that's right. So our FR0 is to control the surface roughness of a 3D part. And the way that we broke this down was into two customer needs, and it's sort of a customer choice, two functional requirements separated. a customer wants to control the surface to make it a finalized part, they're either going to want it rougher or they're going to want to allow it to be smoother. So our two functional requirements are to increase the average peak to valley distance, which if you increase the average peak to valley distance, you're going to make the surface rougher. And if you decrease average peak to valley distance on a micro scale, you're going to make a surface smoother. So those are our two functional requirements. In order to increase average peak to valley distance on a micro scale, we broke that down into increasing our valley depths and increasing our peak heights. And we're going to break this down even more. In order to increase our valley depths, we are going to determine our valley locations first. We've got to figure out where they are by mapping it. We're then going to determine volume of material to be removed, which is going to be approximated by cones, which I'm actually going to go into right now, because this is really the major point of our project. What we're trying to do on a micro scale is to really concentrate on those peaks and valleys and the process, the functional requirement to actually do this type of work. So Mike's going to draw a little thing on the board where you got your surface roughness. And yeah, he's just going to explain it in a little bit of detail while we go through our FRs here.
So we've got a basic app, and hopefully the online students can see this. We've got your standard profile. And the whole point of what we're trying to do is we're trying to measure the surface roughness of the system as a whole. But to break it down and to be able to control it, we have to be able to measure it. So we have a scanning system that scans everything, that makes sure peaks, valleys, distances between it. And it's first got to create a median line. Basically, your set point, where you're aiming for, where your tolerances are aimed at. Then it's got to, depending on whether you're going up with the roughness, down with the roughness, or you're adding or subtracting from anywhere, you have to determine where you're bed. So let's go with you're making the valleys deeper. You have to determine where the bottom of the valley is. Then you have to determine the depth from your median line. So you have to determine from here to here. Then what you need to do is you need to determine your width from valley to valley, and we call that as the diameter between the valleys, so that we can create a volume of material that needs to be removed. So we create an initial cone of material that is there. It's a good approximation of what we need to do, and it helps us because the laser has a focal point. I'm trying to speak.
Oh, God. Thank you. Yeah. You're so right. You jerk.
Hey, I'm sorry. So we've got our initial cone of material that is there currently, the valley that is there currently. Then we use the set parameters by the user to determine how much rougher the surface needs to be to calculate a new maximum depth. We use that maximum depth to then redraw our cone to have a final cone volume. Then we subtract the two volumes to get the amount of material removed. This process can also be inverted to do an addition to the peaks if you wanted to get the peaks higher. So we could do either or.
So there's going to be that software system to be able to determine this. In terms of our end goal here, which is to increase in this case, it's increasing roughness based on that customer need. It's a functional requirement that they want done with their final product, rapid manufacture. So all of this software information is going to communicate this information with our laser material removal, which is right here in FR 1.3. So we're going to communicate all that information over. Everything's going to be mapped. Everything's going to be calculated, and then a laser removal system is going to come in and it's going to take away material out of these valleys. In order to create roughness, we're going to have to increase the peak heights of everything. However, these are going to utilize the same systems, but because we're kind of breaking the boundaries a little bit on the AD here because we're allowing our functional requirements to be controlled by a customer need for their choice. And that's why we believe that that these are uncoupled systems, because based on the software system, the design software, it's not going to allow the coupling there.
You're going to end up with either one choice or the other. You're not going to run all the way through each step.
Mm-hmm. So our FR2 would be, so if this would allow a customer to make their surface rougher by adding the system. FR2 would be to decrease the peak-to-peak valley distances. I don't know if I can. It's not allowing me to scroll. Oh, well. Oh no! Oh, hopefully I can do that. I don't know if that's where that one was. But by decreasing the average peak-to-peak valley distance, we're going to allow the system, the laser system, to let me get this out of here, to make this a lot smoother for these 3D printing. So let's just go back to, there we go. All right, quick physical integration. Ernie's going to finish this up for us.
Trying to go quick here.
Yeah.
So this is just, the process of this design is taking advantage of existing technologies, and basically the innovation behind this is combining everything into one process. So here we have an existing 3D printer, a laser scanner, and a short pulse laser ablator, and the integration would involve combining them. One example could be the use of a 3-headed nozzle, something similar to that. Obviously the wiring is going to be a lot more complex, but that's just an example of how these could be integrated, and they could all move along the same sort of motor system that provides the motion of a 3D printer or a laser. And to go back to the design matrix here. All right, well then I'll just skip it. So yeah, so it gets interesting here with the coupling because, as you mentioned, when you're looking at this and you say you're increasing the average peak to valley distance, it's going to be largely affected by anything that's adding material. If you're trying to make it rougher, you don't want to take material away from the peaks. So when you look at the coupling, you kind of only want to look at FR1, the coupling between FR1 and all the children of FR1 and the DPs of FR1. And when you're looking at the coupling between FR2, you look at the DPs of the coupling between DP 1.2 or DP2. So it's kind of like two different matrices here that you want to look. The only coupling that we really found was through the software system that might be locating the valleys and locating the peaks at the same time. Could be a little bit of coupling there.
I'll go through this quickly. We wanted to compare and contrast Alfredo's system to our own. And this is a direct quote from his European patent, he wanted to produce a superior rapid prototyping system. And he wanted to do that by increasing the usability of rapid prototype parts through external processes. We are specifically aimed at the surface finish. We are attacking one of the processes that he wanted to better through machining, grinding, polishing, other types of external systems.
So in conclusion, we're trying to increase the control, the surface quality, and that's going to depend on, and controlling surface quality, our basis is by the customer need, whether they want it smooth, whether they want it rough, and they're going to allow that choice. And that's where this choice is coming from, and we have our two separate systems to allow that, two separate uncoupled systems that allow that to happen through. All right. Thank you for your attention, guys. All right. Breaking the boundaries.
Yeah, breaking the boundaries. We know it. Yeah, because we're going to try to stay in schedule.
You mentioned the coupling. If you introduced another functional requirement that the user needs to choose, what type of program do you usually want to run with the decoupled system?
Well, it's not about the program, choosing the program itself. The program would probably be a universal program, and say for like you're doing a spree, you already input the feeds and speeds of the cutting tool, and the Esprit program generates the fastest tool path. So you give it the data, you give it the surface roughness, you tell it where it is, so it scans itself, and then it figures out what the best thing is to get to where the customer wants it, what the data that you've input.
So there's an important thing there to design the software.
Yes.
Axiomatic.
That is the key. Is the software.
Yeah. our major decomp is more about the process and how it's going to go about that. The software itself would do the scanning, the mapping, but the actual process itself, like process engineering, is really where we base it. And we've done 6, 7, 8 iterations on it. We've really had this surface quality thing. We've been trying to figure out a process, and we really like this one to figure out the actual process of where it's going to be broken down and how it's going to actually attempt, how it's going to actually control that surface.
Okay, we should
Yeah,
move
sorry,
on.
that's fine.
Okay,
Sorry.
Thank